Hello, my name is Jenna.
Hi, I'm Erica.
And I'm Dom.
And today we're going to discuss how to design a hand warmer using the Flynn Lab.
In this Flynn Lab, we wanted to investigate the energy change accompanying the formation of solutions for common laboratory salts, and then apply the results to design a hand warmer that is reliable, safe, and inexpensive.
First up is introduction. On this slide, we're going to talk about enthalpy, exothermic reactions, and endothermic reactions. When heat is released or gained in a system, it is known as enthalpy. This is represented by delta H. Some compounds, when dissolved in water, produce heat. This heat warms the surroundings and is released from the system. This is considered an exothermic reaction, which makes Gibbs free energy negative, and therefore the reaction is spontaneous. Other compounds, when dissolved in water, gain heat. This heat is released from the surroundings and accepted by the system. This is considered an endothermic reaction, which makes Gibbs free energy positive. Therefore, the reaction is not spontaneous. All compounds release/gain heat in different amounts.
Some background information needed for this experiment are the two units of measurements that are used in this experiment. They are joules and degrees Celsius. The initial water temperature as well as the final water temperature are measured in degrees Celsius. The energy released by the temperature change was then found in joules. Another conversion factor used in this experiment is the specific heat of water, which is 4.18 joules per gram per degrees Celsius.
Delta H, as mentioned on the previous slide, is also measured in joules. The enthalpy of a reaction, or delta H, can have a negative or positive value in joules.
The objective of this experiment was to create a hand warmer that could raise 40 milliliters of water by 20 degrees Celsius using the least expensive of the following solids. The solids include NH4Cl, known as ammonium chloride, CaCl2, known as calcium chloride, LiCl, known as lithium chloride, C2H3NO2, known as sodium acetate, Na2CO3, known as sodium carbonate, and NaCl, known as sodium chloride.
The solids listed were all tested in the same environment as the other solids.
Prior to the experiment, we hypothesized that calcium chloride and lithium chloride will produce the best hand warmers because they release the most heat when dissolved. Calcium chloride releases 82.9 kilojoules of heat when 1 mole is dissolved. Lithium chloride releases 35.14 kilojoules of heat when 1 mole is dissolved. These two will be the most effective in raising 40 milliliters of water, 20 degrees Celsius.
The procedure for this experiment to design a hand warmer was to first set up the MIT certified calorimeter, 2. Measure 40 milliliters of distilled water, 3rd. Place the thermometer in the calorimeter and record the initial temperature of the water, 4th. Measure 5 grams of the specified compound, 5. Quickly add 5 grams of compound into the water and insert the thermometer, 6. Record the highest temperature, and 7. Calculate the molar heat of solution for each compound. Finally, decide which compound works most efficiently and most cost-effective.
This procedure was used for all 6 compounds. However, in between each trial, every material used was rinsed with distilled water. Many safety precautions were taken while completing this lab, such as wearing protective eyewear such as goggles, wearing aprons, and tying loose hair back out of the face.
Based on our data, we were able to conclude that our hypothesis was correct. Lithium chloride and calcium chloride worked the best as potential hand-warming materials. Lithium chloride had an initial temperature of 22.3 degrees Celsius, a final temperature of 50.5 degrees Celsius, and a difference in temperature of 28.2 degrees Celsius. Calcium chloride had an initial temperature of 21.9 degrees Celsius, a final temperature of 42.4 degrees Celsius, and a difference in temperature of 20.5 degrees Celsius.
Sodium carbonate had an initial temperature of 21.6 degrees Celsius, a final temperature of 30.5 degrees Celsius, and a difference of only 8.9 degrees Celsius. Sodium acetate had an initial temperature of 21.9 degrees Celsius, a final temperature of 28.9 degrees Celsius, and only a difference of 7 degrees Celsius. Finally, ammonia chloride actually decreased in temperature rather than raising in temperature. The initial temperature of 21.9 degrees Celsius and the final temperature of 12.6 degrees Celsius. This was a difference in 9.3 degrees Celsius, but was a decrease in temperature rather than an increase. As discussed on the introduction slide, reactions 1, 2, 3, 4, and 6 would all be considered exothermic reactions as they released heat and energy to their surroundings. However, reaction 5 would be considered endothermic as its temperature decreased and it did not release heat and energy to its surroundings.
As mentioned on the previous slide, our hypothesis was correct. Calcium chloride and lithium chloride raise the temperature of the water by 20 degrees Celsius. In order to be most cost effective, calcium chloride should be used because it only costs $10.80 per kilogram, while lithium chloride costs $68.30 per kilogram. On the left, we have a picture of calcium chloride, and on the right, we have a picture of lithium chloride.
Calcium chloride was the third least expensive solid listed, and also the second most effective solid, whereas lithium chloride was the most expensive solid by nearly $40.
As for the error analysis in this experiment, potential errors could have occurred during the measurement of the 5 grams of each compound, as too much or too little could have been measured. Error could have also occurred during the dissolution of each compound as well. As you can see from the graph, you can't always trust all your data.
However, unlike this graph, we were lucky with our calculations and data and did not get any major outliers in the temperature changes that we saw.
In this lab, we mixed ionic compounds in water. However, in future work, this may be more effective and cost efficient if the mixture could possibly be made by mixing the ionic salts and other substances than water. Citations can be found below.